Hello and welcome to Velo Virtual. This is Velo 3D's Application Deep Dive webinar series. Today, we're going to be talking about one of the innovations that could play a role in our next voyage to the moon. I'm really excited about this show. This show has a little bit of everything. We have some topological optimization, metal additive manufacturing, and a mission to the moon. Can't get any better than that. So as a bit of history, just this week, we just found out that this earlier today, this week in 1972, 49 years ago was the last time human beings were on the moon. And a lot has changed since we last visited the moon almost 50 years ago. It was Apollo 17. So the question now is, what is our next trip going to look like? And now that we're able to incorporate so many new innovations in design and manufacturing, what is that picture? So today we're going to get a glimpse into that. As new technologies exist to drive down propulsion costs, speed up time to market, improve performance of different subsystems, the ability of powerful computers to assist with design, simulation, advanced additive manufacturing, to enable new part geometries. This whole ecosystem is offering engineers an entire buffet of solutions that were completely unavailable to predecessors. And the ability to innovate without compromise today is unparalleled. So today we're going to be joined with experts from Aerojet Rocketdyne, Intopology, and of course Velo 3D. And this is going to be a fantastic show. It is an honor to have on the show today James Horton. He's a specialist engineer in systems engineering and mission architecture at Aerojet Rocketdyne. Since 2008, he's held multiple lead roles in rocket engine design, development, test, flight operations for NASA and DoD. His advanced propulsion team at Aerojet Rocketdyne is currently developing chemical, electric, and nuclear propulsion, pretty awesome stuff, to support NASA's deep space exploration efforts. Also joining us today, Ethan Clare. He's Intopology Customer Success Manager responsible for managing the relationship with Aerojet Rocketdyne. He joined Intopology back in October of 2020 after spending 6.5 years with Lockheed Martin Aeronautics, half of that time with the Skunkworks division. So if you're familiar with that group, you know what that means. He's also served as a subject matter expert in polymer and metal additive manufacturing and has managed additive efforts across various programs. Also joining us today is Gene Miller. Gene has held various positions in foundry and process engineering. He joined Velo 3D in 2016 as a process engineer, developing unique laser parameters for our flagship Sapphire 3D metal AM printer. And he was also critical to developing Velo 3D's signature support-free technology. He holds a BS in mechanical engineering from Colorado State University. All right, and with that, James, I'll turn it over to you.
Thank you, Michael, for that introduction. So for those of you that don't follow the space program or not familiar with the space industry, the United States is going back to the moon in the mid to late 2020s. And NASA is organizing this effort under what they call the Artemis program. And so the goal here is basically long-term exploration and utilization of lunar resources. It also has the distinction of being able to send the first woman to the lunar surface, which is long overdue. And because the government's going back to the moon, this is driving a lot of commercial interest and opportunities. And so you'll see commercial companies like Blue Origin, Astrobiotics, Orbit, and many others developing their own lunar landers to take people and cargo to the lunar surface. So when you take a step back, there's going to be a need for propulsion. Basically, how do we get this people and this cargo to the moon so they can accomplish their mission? And so when we look what we did in the past on the Apollo program 50 years ago, as Mike mentioned, we see that storable propulsion and storable propellants were a fast and reliable way to get cargo and people to the surface. And so at Aerojet Rocketdyne, when this opportunity to go back to the moon came up, we asked ourselves, is there any way we can make these storable systems more affordable using technology and advancements over the last 50 years? Because any complex endeavor like going to the moon, the more affordability you can put into your mission or your product is going to help ensure the overall sustainability of your program. So being rocket propulsion engineers at Rocketdyne, we actually really focused on the reaction control system of the lander and spacecraft that would be going to the moon. And so these subsystems are what controls the attitude, or basically the orientation of the spacecraft or lander when it's in flight using rocket thrusters. And when we were looking to what could improve the affordability of those systems, we really honed in on additive manufacturing and its ability to integrate parts and functions, because if we can integrate stuff, we can reduce our part count and we can reduce our touch labor. So we can really start bringing some cost savings into the product. So this presentation is going to recap what we did at Aerojet Rocketdyne in 2019 with additive manufacturing, but with a more traditional approach. And then our partners, Ethan at nTopology and Gene at Velo, are going to talk about how we use their advanced software and hardware to basically take our already innovative idea and iterate it and optimize it even further. All right, this chart is just a little background on what we did back in 1969 on the Apollo program. So the lander, which you can see in the lower left-hand picture, and the spacecraft, which you can see in the lower right-hand picture, had these 100-pound storable thrusters arranged in 4 quads of thrusters around the spacecraft. So in total, there was about 32 thrusters per mission to help orient the spacecraft so it can do its maneuvering and safely get to the moon. Taking a step back even further, you can see, looking at the entire Apollo program, they produced over 650 thrusters to support those 6 moon landings and all the development and testing that came before it. So just the sheer number of thrusters that were produced for those 6 missions kind of led us to believe that we're onto something with looking at the reaction control system. If we can bring affordability there, then we could make an impact on any future program. All right, so the design concept on this chart is pretty simple. You can see in the lower left-hand picture the original Apollo Air design, where they had 4 thrusters, individual thrusters, that were pieced together and then plumbed to bring the fuel and oxidizer to each one of those individual thrusters. And so the idea here is really to use additive manufacturing to kind of take all those individual parts and combine them into a single part and just reduce the complexity of the build going forward. And then we also wanted to incorporate any advances in propulsion technology that we had over the last 50 years. So this is where the MON 25 propellant comes in, and we'll talk about that on the next chart. All right, so this chart, just want to give you a little background on what MON 25 is, because if you're not in rocket propulsion, you're probably not as familiar with it. But when we talk about leveraging MON 25, which is an oxidizer for space applications, what we're really talking about is taking the affordability beyond the thruster and actually applying it at the system level, at the spacecraft level. And we'll talk about why that is in a moment here. But just a little background. So storable propellants we use are monomethyl hydrazine and MON 25, which is the oxidizer, and they're hypergolic. So when the fuel and oxidizer meet, they automatically ignite and combust. And so that's going to give us that reliable restart capability. They're also storable. So when we talk about storable, we compare this to other rocket propellants that you typically see, which are cryogenic, like liquid oxygen and liquid hydrogen. And those, since they're cryogenic, tend to boil off over long durations. So if you want something on a very long duration mission, then storable propellants are key, because you don't have to do any extra cooling or processing to keep them in their liquid phase. So like I said, MON 25, this is where the advancement comes in. And this is because by adding 25% nitric oxide to regular NTO, nitrogen tetroxide, which is a typical spacecraft oxidizer, we can get that freezing point down to about negative 30 degrees Celsius. And what that in turn does is reduces all the mass and power that we need to keep off the spacecraft from keeping the things to freeze in the tanks and the lines. Now, the problem with MON 25 is thrusters that run it usually can be unstable, which is bad in rocketry. And so what we want to do with this design concept that you'll see coming up is we want to start with a point of departure engine that could burn that propellant stably using special injector and design geometries. And so what we've done here, and you can see in the picture on the right-hand side, is we've taken that ICE 100 bipropellant thruster, which we proved could burn stably over a very long test campaign, and then expand that further into the reaction control system. Shows you kind of what we came up with in 2019. You can see in the picture on the left-hand side, a single injector block that has the 4 injectors for the 4 rocket engine chambers using additive manufacturing. And then you just either conventionally machine, or you could 3D print the 4 rocket chambers that would attach to the injector block. And since this injector block had all the complexity, all the plumbing, everything in it, that's what we really wanted to demonstrate in 2019 as a proof of concept. So on the next chart, you can see the results from that effort. And so we're able to successfully fabricate the part, but since we had used a more traditional approach to additive manufacturing, there was some limitations in how we built this part. So as you can see in the pictures below on the left-hand side and in the middle, we had to build the injector at this 45 kind of degree angles because we had overhang limitations on our current industrial machine that we use at Aerojet Rocketdyne. And because of that, we had to add in hard supports that would then have to be machined off later. You can see that in the middle and the left-hand picture at the bottom there where it touches the build plate. We have to go back and machine off those supports, which just adds cost and mass. And the other part is we didn't really mass optimize this design. So you can see in that left-hand picture, we kind of just took chunks of mass out of where we could in kind of this blocky form, but it wasn't optimized to any of the space flight requirements. And we left a lot of dead mass in the thruster. So in space, getting mass out of your system is very important because it takes a lot of money and time and effort to launch every single pound into orbit. So that's where we turn to topology software to help us optimize the design, and then Velo's printing technology to build it. And I think with that, I'll throw it over to Ethan to talk a little bit about how we use the software to get the mass out of the part.
Hey everybody, my name is Ethan Clare. I'm with the customer success team here at nTopology. I currently manage the relationship between Aerojet Rocketdyne and nTop, as well as many other large aerospace OEMs. Like Michael said, I spent a good chunk of my career with Lockheed Martin and the Skunk Works before joining the nTop team. Very passionate about additive manufacturing. Go ahead, next slide, Michael. Today, I'm here to tell you about how we helped Aerojet on this exciting propulsion application. So like James said, our team was asked to help lightweight this component to help drive down that propulsion cost and schedule, and seeing if we could even improve some performance while we're at that. So Aerojet provided our team with the original quad injector CAD. We got pressure and thrust loading conditions. And again, the main goal of this project was to extract as much of that unnecessary weight as possible. We did do exactly just that, by shelling this traditionally CNC part and optimizing it for additive manufacturing. We were able to reduce the weight significantly. At the end of our segment here, I'll talk a little bit more about the results. So to do that, we used first engineering principles to size the walls and the internal tubes. A simple pressure calculation to get stress on the tubes. And we also applied a very conservative factor of safety, about 2.5x, when we were determining the thickness of those shell walls and the tube walls. And for context here, we're talking about 100 pounds of thrust on the face of the injectors and about another 100 pounds of thrust on the tubes themselves. So overall, relatively low pressure situation coupled with a high strength material, made for very little concern in this aspect of the design. So we knew we had to get weight out of this part, and to do that, it would need to be shelled. Aerojet tried to do this in CAD, but when you're trying to shell a part of this size and complexity in CAD, it's simply impossible. It's going to break. Our shelling, booling, and lattice operations are lightning fast in nTopology, so no matter how complex the operation is going to be, you're not going to see a build error like you would in CAD. For this project, we also leveraged a concept that we like to call field-driven design to appropriately size the parts per those loading conditions that I just mentioned. What is field-driven design? That's part of our core technology. I'm going to get to our core technology here in a moment. After I do a quick overview of our technology, my colleague from the NTOP Applications Engineering team, Mr. Evan Pills, he's going to give you guys a quick demonstration live in the software. But first, a little bit more on our tech. So NTOP is a piece of software that enables engineers to consider design, simulation, and advanced manufacturing all under the same hood of a single workflow. So before we get into our core technology, I think it's really important for us to discuss the context in which our software sits within your organization's infrastructure. So this flowchart is really meant to show where we sit within the digital thread and kind of what we bring to the table. So we've got a flow of information in and out of nTopology, where all of that information, data, and geometry goes. If we start on the left, we can import a lot of different things. So as you might expect, we can do CAD geometry, engineering data, material properties. We can even bring in simulations that you set up outside of nTopology. We can port in those results and make use of that information through fields. So the reason why you're using NTOP in very short order is really you can create parts that would be far too complex to ever be able to model in CAD. You can simulate on objects that have lattices and other complex geometries. You can run topology optimizations and much, much more. There's a lot of power under the hood. And it's not just meant to be, a piece of software you're meant to open up and edit, et cetera. We're really trying to capture that engineering knowledge. We like to say that we're almost trying to build a visual programming language that records everything that we do to a given piece of geometry. So as you create more and more processes and workflows within NTOP, you can then reuse those, right? You can share them, you can build intelligence with them. And ultimately, part of our vision is that we see enterprises building basically knowledge ecosystems that can then be accessed from any part of their business or any person in their business. So moving to the export side, we can mesh geometry. We can export certain geometries to CAD. We can export optimization data and results. All of this information can then go into your PLM systems, your CAD systems. It can even, like I said earlier, it can even go out to other simulation and CAE tools, which is really quite a common practice we see our clients doing. It can also go direct to print, right? So we can get slice data out, we can get mesh data out, and we can produce all sorts of parts directly from the complex geometry that you just generated inside NTOP. So to wrap up this slide, I think the key takeaway here is that we're here to integrate with your digital thread. We are certainly not here to replace CAD. There's stuff that CAD is definitely really, really good at. We recognize that, but it does have its limitations. So, those complex CAD operations that fail all the time, like your Booleans, offsetting, shelling, unioning, what have you, this is really where nTopology excels. All right, so to cover our core tech, here at NTOP, our value proposition is really built upon 3 core technology differentiators. The first of which we lovingly call unbreakable geometry. So this is our unique implicit modeling kernel here at NTOP. This is the native geometry format for our software. And we're representing geometry as implicits and fields, right? So because of its lightweight nature, representing as implicits and fields, your operations are going to be lightning fast. They're going to consume low amounts of memory, and they're going to be very, very efficient and really never going to fail. So no matter what input that you put in, you're not going to see any build errors or downstream errors from an operation that you did, perhaps merging, unioning, or one of those other complex operations. We build that in a really, really robust way in NTOP. For the second technology differentiator, I'm going to jump to the right-hand side of the screen, is this concept called field-driven design. And this concept is really inspired by how things work in the real world, right? In the real world, there's physics, mechanics, thermodynamics, and these things are not defined as discrete values at discrete locations. They're fields. And in fact, most things are fields. So when you have a design tool, as an engineer, you're often having to take a field and sort of discretize that and put that into your part design. Our goal at nTopology is to connect fields directly to geometry to enable users to directly influence design. And we're very, very good at that. So any parameter that you can think of, you can control that with a field inside nTopology. And really what's so powerful about this is that it enables, a paradigm shift in the way that we go about designing new products. For example, if we utilize CFD and other simulation data from the onset of a design, we can have a significant impact on the overall performance of that part or of that system. And finally, for the third and last core tech is this concept we like to call reusable workflows. So with these other two things, with field-driven design, with unbreakable geometry, it really powers this third concept, which is reusable workflows. So from the start, nTopology was built to be able to capture engineering knowledge. You've got an engineering notebook that defines how the inputs to your system produce what outputs. The thing that field-driven design and unbreakable geometry allow you to do is take only a few key inputs to your notebook, put them in their own dedicated input section of the notebook. You take all of this information and you package that up into a single workflow that you can then share with colleagues, your team, or even the whole company if you want. So with that, now you can hand this off to perhaps an inexperienced user, or even somebody that's not interested in learning all the intricate details of a new software. And they could come in and they could say, okay, here's my CAD, here's the stress, the stiffness, or whatever they want to apply to that geometry as a field. And they can produce that, the resultant geometry within just a few set of inputs. And this is really powerful because not only is it convenient, but let's say you're doing design variations, or you want to do a design study, or you want to perform some sort of iterative process where you look at a bunch of different lattice types, lattice configurations, or different CAD geometries. Maybe you have a revision on a part. You can keep all of this process locked in with our software and just drop in your revisions to your CAD or your design variations, etc. So that was really a very quick technology overview of nTopology, but definitely needed before we get into the live demo. At this point, I'm going to hand it off to my colleague, Evan Pills from the applications engineering team. He's going to give you a quick demo, quick overview of the design process that we took on this part. Evan, take it away.
Awesome. Hey, thank you, Ethan. I just want to do a quick mic check while you're still there, making sure I'm all sounding good.
You sound
great.
Fantastic.
All right, wonderful. Well, thank you for giving that quick overview. It certainly makes my job a little bit easier, but what I want to do is take you through what we did inside the software at a pretty high level, right? I'm not going to get into the extreme nitty gritty, but I want to take you through all the steps we did to end up with this really nice end part here, right? We have this latticed infill geometry, it's shelled. And at the end of the day, the main thing is it was easy to do, right? That's the big thing. All right, so let's go back to the beginning. All right, we started out from this CAD. We had the wonderful people over at Velo and Aerojet go ahead and send this over to us, right? And what we did was a little bit of defeaturing here. We filled in this volume because what we know we can do is take this, and you'll notice this is CAD data, right? Ethan was explaining implicit modeling and everything like that. There's no faces and edges and points with implicit modeling, but we're here to play with all those tools. So we're going to start in CAD because we can design this in CAD, much easier than we could design it in other tools. Then we're going to come to nTop and do this difficult work. So the first thing I'm going to do is I'm going to take it from CAD data. I'm going to turn it into an implicit model, right? So all of the data, the entire geometry is the exact same. It's just being represented as an implicit now. And because I have it represented as an implicit, I can go ahead and throw it into our shelling operation and immediately shell this geometry without a second thought. It's a very complex shell. We have all these fluid paths and injectors and everything happening on inside of here. And in one single step, one single block over here, I'm saying, okay, go ahead and shell my part. You know what? Why don't I remove the top face as well? And I want a 2.5 millimeter wall thickness, right? And that's a uniform wall thickness, but with that field-driven design Ethan was talking about, doesn't always have to be. So now we have this really awesome shell inside of here. But before we moved on to the lattice, I went ahead and said, okay, there's a couple areas in here. We have some sharp corners here. We have some sharper features in here. So why don't we take care of that? Because again, with implicit modeling, that's something we can do. I don't have to click on all these little edges and hope the fillets work or anything like that. I'm just going to do a couple of operations in nTop corner areas, but where the injector fuel paths are, need to very easily put these blends to immediately get rid of any of those stress concentration areas, or at least reduce them by a significant amount with very little work. And now I have this shell volume, right? So we removed an extreme amount of mass by shelling this geometry. Is very easy for us to do, very quick to do, but it's not quite strong enough anymore when we just shell it like this, right? So what we want to do is go ahead and infill this internal volume here, right? And I have this highlighted blue. If we go ahead and take a section cut, you can see this is the volume here that we initially removed. I'm going to take that volume and I want to infill it with a lattice. And that's something NTOP does extremely well, is creating these sorts of lattice structures. You can just go ahead and I created this lattice structure here. We'll put it back on here so we can see it inside of this part. All right, and we're able to create this lattice structure. And this lattice structure does several things for us. One, it's stiffening our part back up, right? We want to work with a bit of a factor of safety here. And we actually designed to a pretty good factor of safety inside of here. And we did that with this lattice structure because this lattice is going to give us supports in all directions, right? This is a periodic lattice. It's actually, cubically symmetric. So we can go ahead and make sure it's supporting us the same in all directions, supporting our part, adding that stiffness that we might have lost from that shelling operation. But it's also going to go ahead and take care of printability issues in some cases here, right? We have some unsupported overhangs here that might cause some problems. This lattice is going to go ahead and help us out with that as well. So we're using this lattice as a bit of a multitasker in this case. But we didn't just infill this with a lattice structure. If I take a look at this part from the top, we actually went ahead and infilled this with a varying lattice structure. So something that you can do inside of NTOP is what we call field-driven design. And Ethan gave you guys a bit of an overview of that. I'm just going to show it off here. And what I did was I created this field to control my lattice structure geometry. So instead of a uniform beam thickness, what I did was I placed an axis which goes directly through my part. And you can see if I highlight this axis that goes directly through the center of my part. And I'm using the distance as I move away from that axis to vary parameters of my lattice structure. And in this case, if we take a look at the very center of my axis here, I have a 0.5 millimeter beam. And now radially, as I taper away from this, I am increasing my beam thickness, therefore increasing the strength or the stiffness of my part at the end of the day. And because I'm doing it radially, right, we're not having big effects on anything like center of mass or anything like that. So this is a really nice way to be able to control our geometry. And it's a very easy thing to do inside of NTOP. You have a nice smooth transition from nice thin beam to nice thick beam, and it is all being applied to this lattice structure without a second thought. And that's the best thing about NTOP is we can do these sorts of complex things. And then to Ethan's final point is, we didn't end on this final design on our first go, right? We had to go through a couple of iterations. And with NTOP, if we want to change something, right? Let's say we want to change from, just do a drastic example, instead of a body-centered cubic unit cell, which I can highlight over here, maybe we wanted to go to something more like a gyroid unit cell, right? What if we wanted to do that, right? That's not what we're doing in this case, but with NTOP, what I could go ahead and do is just swap that out. And at the end of the day, NTOP is going to generate me a full new lattice structure following that same variance that we've created here right away, right? You don't have to redo any of the work. So what I'm trying to show off here is the fact that with NTOP, it's really easy to explore this design. So it was very easy for us to create these geometries, explore them, and then optimize them. And that is the entire goal here. Right, so that is a high-level overview of the workflow from start to finish here in NTOP. And I'd love to hand it back to Ethan to kind of give you guys a summary of the fantastic results we got out of what we did here in NTOP.
Thank you for that demo, Evan. To wrap up the NTOP section here, I'm going to talk about the results here. So recall that our primary goal of this exercise was to eliminate as much unnecessary weight as possible. We did exactly what we set out to do. So by shelling this part and filling it with that lattice structure that we just showed, we were able to achieve a 67% weight reduction in just a few design iterations, right? So arguably, if we had a little bit more time, maybe we had more resources and efforts to do more iterations, I'm pretty confident we could get even a little bit more weight out of there and further optimize this part. Secondly, by leveraging our implicit modeling technology, we were able to drastically reduce the design cycle from weeks to hours, right? So all those complex operations we talked about, shelling, latticing, you just saw how extremely quickly we can perform those order operations in NTOP and do so without failure. So secondary operations like maybe blending those lattices to the outer shell or applying variable wall thickness or variable beam thickness to your lattice, those are completed just as fast and can be iterated quickly based off of maybe simulation or even real life test results. So lastly, we talked about field-driven design. We talked about kind of the paradigm shift in the way that we go about designing new products, right? So by utilizing things like CFD, stress data, and other simulation data as early as possible in our design process, we can have a significant impact on the overall performance of our in part or in system. We can converge on those optimum performance designs quicker if we do this. So with that, I'm going to wrap up our section. If you have any questions about Intop or our technology, we'll be happy to address them in the Q&A. At this point in time, I'm going to hand it off to Mr. Gene Miller from Velo3D.
Thanks, Ethan. Hey, everybody, I'm Gene. I print stuff. My main goal here is to take all that hard work and all the really unique characteristics and optimizations that Intop and Aerojet put into this part and actually turn it into a real tangible metal component. And that's what we're going to talk about today, why it's challenging to be manufactured by other means or impossible, and why it's able to be manufactured on a Velo Sapphire and our end-to-end solution. So next slide, please. So let's talk about this part and why it's a pain. If you can machine this part, you get a gold star. I don't know how you do it. You've got all these internal features that would be very challenging to reach, as well as the lattice structure that it's practically impossible to machine. It's then even so challenging to print on a more standard metal AM platform because of all of the internal channels, the low angle closures, these very delicate lattice features that would be subject to recoder contact and might be problematic in a traditional metal AM platform. There's also this big pain with printing titanium. Titanium prints very hard and very brittle, so you run into a challenge of cracking. And Velo has come up with a very unique way to mitigate these stresses inside the printed material, such that we don't have to worry as much about cracking of titanium in the printing process. So how do we do this? I get the question a lot, hey, so you can print low angles because of the process, right? Yeah. You can print low angles because of the hardware, right? Yeah. You can print low angles because of your software, right? Yeah, it's all three things. And all three things are working together in order to enable the printing that we do today. And it all starts with the Flow software. That is our proprietary preprint software that we made to work in harmony with the other tiers of our end-to-end solution. That is where we do all the print preparation. We add support material if needed. We can add process overrides and create a Velo print file. And that print file is then loaded into the Sapphire printing machine. That's where the proprietary hardware goes to work. And actually printing of the material occurs. And that machine is just loaded with sensors and gathering data. And it wouldn't mean a lot of valuable sense if it weren't compiled in a digestible form. And that's where the Assure quality validation software comes in. That takes all of that data that was gathered in the printing process, as well as the health metrics that we capture on the machine, and deliver it in a digestible form for the end user as for a quality validation and good peace of mind that they received a quality part. So there are 3 different sizes in the Sapphire printer family, all of which are using the same hardware, the same processes, the same software. Everything is very scalable from one machine to the other. It's just different sizes and different print productivity. Each are using our 1 kilowatt lasers, and all are capable of doing that same in situ laser alignment that we can use on any of these parts. All are using an argon inert environment. We have that standard 50 micron layer thickness. The one-click calibrations that I mentioned earlier, they are all easily done by the technician. We don't need to do additional hardware or sensing equipment that needs to be loaded into the machine. This is all done as a quick check before each print or in a weekly cadence, whatever the owner or operator of the machine can dictate that. And then the in-situ monitoring from those 900 sensors are all built into each one of these machines and gathering data throughout the prints. Ready to go right out of the gate today are a few Inconel alloys, Hastelloys, titaniums and aluminums are ready for production right now. We're printing in these today. And this part in particular that we're talking about today was a titanium 6.4 part. Coming soon, next on deck is our GR COP 42. That's a big one for the space environment, as well as some stainless steels and aluminum 6061. And our whole strategy here in material development is really driven on interest in machines. Customers that want to buy a machine on a new alloy that we haven't explored yet, if it's weldable, theoretically, it is metal 3D printable. So we would do that material development in parallel with the lead time that it would take to deliver the machine. So if you want a new material, we do it free of charge and just deliver it with the machine. So keep that in mind. What are our specific capabilities with this low angle process? I love printing dome closures because we can get away with bloody murder. The way that the shape compiles on itself, the stresses really work in our favor. And we can print some really large dome closures, well over 150 millimeters. To be honest, I don't think we've even found the true limitation in some cases of what we can print unsupported because of the diameter of the build plate. Once we start printing these types of dome closures on the larger XC Sapphire, I think we're going to finally find our limit as to what we can print and find the limitation of the process, not based on the limitation of the size of the printer. Horizontal holes, another unique unsupported strategy that Velo can play with printing up to about 100 millimeters of diameter without the need for support material on the inside. Tilting that hole opens that up to well over 100 millimeters. We can push that envelope much higher just with a slight tilt of the tube. And it does have, there are other geometric concerns in mind, but the minimum thickness that we can resolve there is about 0.5 millimeter, 500 micron. And horizontal spans, if you want to print a small gap or a bridge, we can span about a 10 millimeter gap. And the smallest gap between the two before your two walls start fusing together is, again, that 500 micron mark. So I get the question a lot. So what does your downskin surface look like? And I think this is one of the best examples that we have of an as printed downskin printed at 3 degrees. We quantified this to about 15 micron SA across that bottom skin. And what you see is what you get. This is right out of the printer. We didn't polish it. We didn't do any surface, no bead blasting or anything. We just cut it off the build plate, and this is what you're looking at. So you can expect this on a low angle overhang that is operating nominally. So we get a lot of questions again about the non-contact recoder and how does it work? And without going into excruciating detail, it's similar, but more revolutionary than just a traditional like snowplow or dump and smear type recoder. We are dispensing powder across the whole powder bed. And then there is a blade that comes and normalizes that surface, makes it nice and flat for it to be addressed by the proprietary powder removal tool. And that is removing all but 50 microns of powder. So that then what's left is our feedstock for our next layer, which is uniform 50 microns. We'll go through the next slides kind of slowly, and I'll talk about what's happening here. So first, the recoder is getting ready to address the powder bed. And if we go to the next slide, now we're starting to dispense the powder in a thicker form than we're going to need. But then you can see the blade comes right behind it and so scrapes it smooth. And then the proprietary powder removal tool is removing all but that 50 microns of powder that is then left on the powder bed surface. Now, what's unique about this is we can allow some protrusions to occur to a certain level, of course, but we can let the metal bulge up to some degree. And that's actually tuned in with our process. We design our process to do that. And it is enabled by our non-contact recoder. So you couldn't use our proprietary laser techniques on a traditional recoding mechanism because of this. So to quantify these protrusions, every layer we have the height mapper. It's a scanner that maps the entire surface, and this happens every layer. This is all recorded in the machine and then reported in Assure. And this is on the left an example of a nominal powder bed after that layer has been processed by the laser. And what you see on the right is after a crack or a protrusion had occurred. So in this case, the height mapper recognized the high point on the powder bed. And that circle is not we didn't PDF that in. That's not a Photoshop circle. That's automatically put in by the height mapper in the logic that will actually pause the machine and say, hey, I need a user intervention. Please let me know if I need to scrap this build or if we can recover. So it's something that's really, really advantageous to have this technology built in to avoid that recoder damage because, hey, I don't want to have to replace a recoder if I don't have to. Onto Assure, the quality validation software I mentioned earlier. It's really compiling all this data in a digestible form. You can use it for real life fleet tracking on any of your machines at your facility. You can look at the active build that's printing at that very moment, or you can also go back in time and look at historical data. The tool health checks that we talked about earlier, those are all recorded in Assure, and the health of the machine is reported in that build document that is available to the user. And also the in-process monitoring, all these data that are gathered throughout the build are all stored in Assure. And if you want more data than just the build report at the end, you can output the raw data and really dig into the nitty-gritty of what's happening in the machine. The build report, however, is just a really concise, clean way to see that nothing went wrong in the print, or if there is something wrong, you know exactly what it is and where to look. So in Flow, the preprint software, we have recipe assignment, and this is something that's done automatically by the software. The software is intuitive enough to recognize these geometric features and apply specific laser parameters to those areas so that they print without the need for added support material, so that they print as efficiently as possible. Areas like a bulk parameter, you want a high throughput laser process. For low angles, you want something with maybe, say, a lower power, but the ability to resolve these low angle features without the need for support material. In this case, we have a really unique ability to recognize the LTCX file, the lattice file that is generated in Anthropology, and apply a very specific laser parameter to that. And this is all done automatically in the software. One thing I will mention here is the stress relief or stress reduction. We have the ability to print this Ti-6-4 material without the incredible stress risers that exist. We have a way to mitigate the stress inside the printed material, and we aren't as plagued by cracking problems as in other materials or other printers printing the same material. You know, scalability is a big concern, especially when we're printing one part and want to print it a lot of times. I remember that James mentioned that they made 600 of these thrusters, and you know, it would be a headache to say, I've designed this one print file, I want to print it again on a different printer. Then I need to make compromises and offset differences, et cetera, and make a different print file to print on a different machine. Because Velo goes through such an excruciating qualification process, and we do such a good job with that, and we have these weekly tool health metrics that we're checking the health of the machine, we can maintain the knowledge that we know that this same print file that printed 2 weeks ago on a machine in Austin, Texas, can be used on the machine in Japan and print the same print file. And that's something that I think is really vital for the scalability of Metal AM moving forward. So it really, it really opens up the door to what we can produce in multiple locations on multiple machines. So this is it. This is the printed part in the flesh. The titanium lattice was resolved very well through our printing process. The laser parameter that was applied to that is different than all the others that are on the part. The internal passages were supported by these lattice features, so we didn't need to add any support material on the inside. And again, we didn't have the problem with cracking of the titanium. So with that, I'll hand it back to James, and he'll take us across the finish line.
Yeah, thank you, Gene. So I think what we've kind of shown here today is that if we leverage kind of these advancements that we've made even over the last decade in additive manufacturing with software and hardware, we can really take that and interject affordability and even improve upon the performance of the way we used to build parts in the past. And so what's exciting for me is that we were able to actually demo this proof of concept. And so now I'm pretty excited to start taking this and trying to bring it into actual testing, actual hot fire testing, so we can then put it hopefully up into space. And so I think with that, we're going to open it up to questions and answers now. So Gene, Ethan, and myself will be happy to take your questions.
Absolutely. Thank you, everyone. Great job presenting today. I'll go ahead and address the first question that we get asked most of the time, and that's, will you get the slides or will you ship the slides? So in general, we don't send out the actual slides. What we will do is, this session is recorded. We will be providing a recording in about 24, 48 hours. So it gives a little bit of time to do the processing on the system and get that to you in an email. You get a direct link, so don't have to register again or anything like that. And please feel free to share that link. It is on YouTube. It's publicly available. So that's the first question. So while we wait for a couple questions, I do have two here. One of the questions kind of coming in is maybe for Gene. Do you have any customers using this golden print file, and can you talk about that a little bit more?
Yeah, actually, I'm glad that came up. This isn't something that we're saying we can do. We are actually doing this today for several of our customers at several of our different contract manufacturers across North America. And we are seeing that the quality is there. The customer is satisfied and pleased with the results. And you might see some things fly into space that have done this at some point in the near future.
And there's a follow on here. What contract manufacturers have these systems available, or does the customer have to buy the whole platform in order to print parts?
No, I mean, we're in the business of printing parts and establishing the demand. If you want to print parts, you do not have to buy a machine. We have a slew of contract manufacturers across North America, Asia, and Australia that have these printing capabilities and can deliver turnkey parts without the need for the big investment of buying a whole printer. And we'd be happy to hear about any parts that you might have and have the need to produce.
Okay, one a little bit more application specific. Looks like Josh is asking a couple questions here. Can you comment on the print time? And then was any analysis done for dimensional accuracy of the print versus the original CAD? And what post-processing was used for the block, or would be used if it hasn't been done yet?
Yeah, so the print time on this was a pretty quick print. If I recall, it was about a day and a half, somewhere around there. And we printed two, the side by side on the build plate. I think you could even fit more if you really wanted to. But then, as far as dimensional accuracy, I don't think we did any scans yet of this part. But that's something that we could easily do. I don't see a lot of dangers in really the deformation, because this part was kind of chunky. It was right on the build plate. There's not a lot of opportunity for deformation until you actually remove the part from the build plate, which we really minimize that by doing a secondary heat treatment, which is just to really equalize all the stresses inside the part so that you don't get a potato chip peeling off the plate. That was really the only post-processing that was done to this part. We cooked it in an oven for a few hours. We EDM'd it off the build plate and maybe cleaned up some of the sharp edges with a file, but that was about
it. And I don't know, maybe James, if you have anything to add to that, what additional steps you would make in the manufacturing process?
Yeah, so typically when we make these for actual hot fire, not just like a proof of concept demo like we did here, we'll go ahead and use a structural light or a white light type inspection just to check for that deviation. And there's a few other inspections that we'll do. Like, obviously we have to proof pressure this part because the propellants are coming in at pressure, and then obviously that will give us a leak check of the part too, to make sure that the propellants, or in this case whatever water we're pushing in to leak check it, isn't going to rupture a line or burst out the part. So there are a couple standard steps we do take when using these in actual operation in hot fire.
All right, thank you. There's a question here. Can you describe how you control the quality of the printing of the lattice structure? He points out this is always tricky.
No, that's a good point. That's a good point. In the printing process itself, I think a lot of traditional AM platforms are struggled by the typical recoder that's bumping into these delicate lattice struts every layer, and we have that advantage that we have no mechanical contact with those thin little beams as they're being printed. So the visual aspect of the lattice when it comes out is very obvious, that it's very smooth and consistent, and there are no step lines. There's no evidence of powder being flung around during the print. And then also, the initial qualification of the lattice process is what we, roll into the flow parameter, and that's validated internally before it's ever released to any of the customer-facing versions of Flow.
Awesome, thank you. There's another question here for Gene. Does the Sapphire family of printers have the capability to vary the laser power along a single stripe vector?
Theoretically, yes. I'm not sure why you would want to, but what I think they might be getting at here is, say we're printing a feature that is over a substrate, and then as something goes in an overhanging geometry, you might not be able to dissipate heat as well through that shape. And what I will say is that our family of recipes, or our process recipe library, will account for that. We do have varying laser powers over lower overhanging features to reduce power, to reduce the likelihood of over melting of these features. So that's something we've rolled into the process.
There's another question. You mentioned variable power. Are you varying the power during the print?
Yes, but we don't use feedback from the thermal detectors. That's only just to gather data. We don't modulate the power based on any of that data. It is a lockdown process set that does not change. However, based on those processes like bulk process or low angle process, those do have different powers, but they're not changing throughout the print.
Awesome, very clear, thank you. All right, one more. Okay, so this question is about part-to-part variability, which I think you mentioned before. Let's see, in this type of part with mixed structural elements, what are the various elements that you control through the qualification process? They mentioned some speeds and feeds here, the lasers, process power, in situ material test coupons, etc.
So for a full qualification of this part, I mean, that's something that we would work with probably Aerojet Rocketdyne and any other governing bodies that would be to really say, hey, let's qualify this part for flight hardware on a spaceship that we're going to put people on. That's something that is in the forefront of our minds when we design these processes and our hardware to really comply with these. To say that we've gone through that yet on this part is premature, but I think we can get there. And knowing that we do such a good job with qualification internally, I think that's going to scale to external qualification. We just have to do the legwork to get there. And it's a long road, and we have to do our diligence with that. But we would have to go through it with a fine-tooth comb and address all the specific needs of the final application, Aerojet Rocketdyne, and the final governing body, whatever that may be. So that's a very open, big question to answer.
So we do have a couple more questions coming in. What I would say is that if you do want to have a longer conversation with us, please reach out at info@velo3d.com. We can go into a lot of depth that we might not be able to do here, and we are coming up on the hour. I do want to give a little bit of time for our speakers to have final thoughts. And maybe James, if you can kick it off, what are your final thoughts from the project, and what are your main takeaways?
Yeah, no, I mean, going into this, I didn't even know if it was possible to do this type of integration. And I think, what we've shown is that this is a viable path to kind of, affordability, reducing the part counts, reducing the touch labor that goes into typically what would be a heritage design, that was done 50 years ago. So just going through this process, working with N-Topology on the optimization, and working, with Gene and Velo on the hardware side, I've learned a lot, especially since my background is not material science, and I'm looking forward to trying to bring this product into actuality and using it in space. So that's kind of what we're working towards right now, is let's get this into hot fire. Let's show that process control can work to produce these parts, and let's get them flying. So my final thought. Thanks.
Awesome. Ethan, we'll rotate to you.
Yeah, just want to say thank you for everybody's time and attention today. It's an honor to be partnered with, Aerojet and Velo on this project, working on exciting things like going back to the moon, right? When I looked up how much it costs to launch a pound of anything into space before this, and according to NASA, it's $10,000 per pound. So anytime we can get 67% of weight out of a product and help our customers like Aerojet deliver value to their customers, drive down costs, and overall be more efficient, more effective, that's what makes our jobs exciting. So really glad to be a part of the project. If anybody is curious about NTOP, our contact information will be going out with what Michael sends out. Just as Michael said, in terms of Velo's technology, we can get really hot and heavy into NTOP for hours. So if you're curious about that, set up some time with us. And thanks again.
And Gene, we'll let you close up.
Sure. I kind of just reiterate what James and Ethan are saying. Super excited to be a part of this effort and really, enable the optimization like we can. Like my experience is working in the foundry, where it was my job to say, no, we can't do that. You're gonna have to change that. Think again. Not gonna work. And now in this new platform of manufacturing, where I have the ability to say like, oh yeah, we can do that. That's fine. And let's put it on something that's going to help us get to the moon. It's really rewarding and fulfilling and exciting. And I'm just, truly privileged and honored to be a part of this effort. And I can't wait to see somebody land on the moon. And if they're flying some parts that I can print, oh man, just a bucket list goal there. That would be awesome.
That is going to be awesome. All right. And thank you, panelists today. Y'all did a great job. It was an amazing session. I had a lot of fun hosting this today. And thanks for the attendees who joined us today. Great questions. If you do want to know more, please reach out to us. We love having conversations. We'll talk your ear off. We love talking engineering, or at least Gene does. or one of our Gene clones that we like to print Gene clones here. So yeah, reach out to us. Let's have a conversation and get into those concerns and resolve them. But yeah, thank you again, everybody.
Thank you.
Thanks, everybody. See ya.
Thank you.